Hello, teacher Morales. We are the group that is going to talk about the Cohen method. Uh, First, the Cohen-Coon method is a classic technique to tune PID controllers proposed by George Cohen and Mr. Coon in 1953. It was developed shortly after the Ziegler-Nichols rules. Uh, what is the Cohen-Coon method? It's an empirical tuning technique for PID controllers based on the approximation of the plan to a FOPDG. That means first order plus the time. The performance is expected that the uncontrollability factor should be greater than 0.3 to apply this method. This method shows a reasonable performance for uncontrollability factor values between zero point 0.6 and 4.5. The robustness is when the uncontrollability factor is less than 2. The plan is easier to control. The delay doesn't dominate much. In this case, Cohen tuning, which is a receipt.
I'll talk about the advantages and disadvantages of Cohen-Cook method compared to Ziegler-Nichols. With respect to advantages, this method offers a fast and practical initial tuning based on a planned data. It's simple to apply and doesn't require complex modeling. By working in open loop, the process stability isn't at risk during identification. This method considers desk time, which usually improves response speed for processes with higher delays. It results in shorter settling time and reduction of offset in a steady state. Next. Next slide. On the other hand, the disadvantages are that X formulas generally produce aggressive tuning with high proportional gain and short integral time. If the estimating model isn't accurate or if the process varies, Cohen-Coon tuning can lead to considerable oscillations or even instability in the closed loop. This method is directly applicable to processes approximately of first order with text time. It doesn't consider noise or changes in operating conditions. It requires an open loop test to obtain the reaction core, and finally provides a quick starting point. In practice, it needs further fine adjustment to guarantee robust stability.
Well, continuing with the example, in this example, we work with a heat exchanger whose dynamics can be represented by transfer functions. Two paths are modeled, one for the effect of steam flow and another for the disturbance coming from the inlet temperature. By combining them and linearizing the exponential delay term Euler to the minus s using a PADI approximation, we obtain the equivalent plant model. This plant shows a small gain, several poles in the denominator, and a zero in the numerator, which reflect both the system delay and its thermal inertia. Next. To apply Ziegler-Nichols closed loop tuning, we first need to determine the ultimate gain, KCU, and the ultimate frequency, WU. In MATLAB, we use the command margin G, where G is the transfer function of the plant. The results were an ultimate gain of approximately 143.46 and an ultimate frequency of 0.587 radians per second. This value represents the point where the systems under poor proportional control reaches sustained oscillations. Next. With these values, we apply the Ziegler-Nichols tuning rules. First, the proportional gain is adjusted as KCU prime equals to KCU over 1.7. And these expressions will we use to calculate the integral time, the derivative time, and the ultimate gain. With these correlations, we can apply in Simulink with the P, I, and D controller parameters. Next. As you can see, we implemented these parameters in the Simulink P and ID block. In the configuration window, we entered the proportional, integral, and derivative values we calculate using the parallel form from the PID. This allows us to run the simulation and observe the plant's response to a set point change or a disturbance.
Well, for the Cohen-Coon method, we need to apply the Cohen rule to reduce the plant equation. In this one, we use the rules, the Cohen rule, to get the gain, which is the same as the first plant. The tau is the higher tau plus the second higher tau, which is 4 divided by 2. which equals 12. And the dead time is the second higher tau divided by 2 plus 1, and which is the dead time from the previous equation, and this equals 3. And in this method, we can get the reduced plant. Next. To apply the Cohen-Coon method, we use these equations. In these ones, we can get the proportional gain, the integral tau, and the derivative tau to the P, Pi, and PID forms. We're going to use the PID, which is the same that we use in the Ziegler-Nichols method. Next. Well, for the use of Cohen-Coon method, we use the previous equations to the proportional gain. We replace the gain, the dead time, and the tau we calculated before, and we got the 52.67. Sorry, for the integral tau we get 6.7, and for the derivative tau we get 1.04. Next. Well, with these equations, we can realize the PID tuning using the Cohen-Coon method. We got that the P is equal to the proportional gain, the I is equals to the proportional gain divided by integrative tau, which is 7.86, and the D is equals to the proportional gain multiplied by derivative tau, which is 54.78. Next. And to the tuning, we write these parameters that we calculated before in the Simulink for the proportional, integral, and derivative ways.
In Simulink, we first scope the original plant, which is a second-order transfer function. After recording its step response, we applied Skohenstadt reduction to obtain a first-order plus dead time model, FOPDT. Our goal was to obtain a simplified model so we can apply the Cohen-Coon PID tuning model. Next. This figure shows the Simulink scope of the original second-order plant compared with the simplified FOPDT plant. When we compare both graphs, we can see that both of them show very similar behavior because rise times are set and settling times are almost the same. Also, we identify that the small difference is in the initial dynamics because the reduced model Skohenstadt rises a bit slower at the beginning, but then it matches well with the behavior of the complete model. This confirms that the Skohenstadt order reduction is a good approximation since it keeps the main dynamic characteristics of the system, making the PID controller tuning easier without losing accuracy in the overall behavior. Next, now with the obtained FOPDT plant, we can make the Ziegler-Nichols model and the Cohen-Coon model control loops on Simulink. So we can compare the control loop performance and its stabilization for both methods. Next, this figure shows the Simulink scope of the Cohen-Coon and Ziegler-Nichols PID tuning for control loops. And we can see that both responses are oscillatory, but with clear differences. For example, Ziegler-Nichols model is faster to reach the reference, but with higher initial overshoot and more pronounced oscillations. And Cohen-Coon shows a more moderate overshoot and a slightly more stable behavior in comparison, although it's still oscillatory. In steady state, both methods drive the output of the same final value with an error approximately equals 0, which confirms that both methods adjust the integral correctly. Next, to conclude, the Cohen-Coon method is still a reference tool for PID tuning since it brought a significant improvement compared to Ziegler-Nichols by explicitly including that time in its formulas. Its main contribution was to provide direct analytical formulas based on the FOPDT model, which allows an initial tuning without depending on the ultimate oscillation tests, reducing risk in the industrial practice. This method works reasonably well for controllability factors between 0.6 and 4.5, but its robustness is poor when the relation between that time and the time constant is below 2. In those cases, it tends to generate too aggressive and less safe adjustments, which confirms that it was designed for processes with relatively large delays. And compared with Ziegler-Nichols, Cohen-Coon typically delivers faster settling and smaller offsets for delays-dominated processes, but at the cost of reduced stability margin and greater sensitivity to modeling errors. Thank you.